In a very similar way to how we evaluated double integrals, we would start with essentially a multivariable function, a two-variable function, and we could integrate with respect to x and y separately and in any order. In a very similar fashion, we could extend that idea into 4 dimensions by integrating a 3-variable function with respect to x and y and z individually. So let's take a look at what this would look like in a way, even though we can't really visualize a 4th dimensional object. Let's just assume that we have this lump of clay, this blue lump of clay here. And if f of x, y, z is some function that's defined on this closed bounded region that we call D, so we're calling this turquoise region D, then we could fill D with small little rectangular cubes that all have a delta x and a delta y and a delta z. And obviously the volume of that cube, that small cube, would be delta v equals delta x times delta y times delta z. So our goal here is to be able to find the volume of this entire region, but integrate the multivariable function, the 3-variable function, times delta v. So we can see that as the largest of all those little teeny cubes approaches a volume of 0, then that must imply that the number of little cubes that we're filling this lump of clay with is approaching infinity. So it turns out then that if we wanted to take the sum of all of these 3-variable functions times their corresponding delta v, which means that if I were to look at this particular point right inside of this particular cube, that point in 3 dimensions would map to a 4th dimensional function value. And if we were to multiply that function value times the change in volume, then this simply becomes a triple integral, dv. So we could see here that if this is dv, that there are actually 6 possible orders that we're going to be able to integrate using a triple integral. It depends on the function, whatever, we would probably pick the variable first. That's going to be the easiest function or the easiest function to integrate, or whatever we just feel is going to be the easiest of them. So we could integrate dx, dy, dz, or we could integrate dx, dz, dy, or of course dy first or dz first, and so on. So that's why we have 6 different options. Other than when we were doing double integrals, we only had 2 options, either dx dy or dy dx. So let's take a look at an example of how we can actually calculate a triple integral. So it asks me to evaluate this triple integral over a region D of this multivariable function. So we should see that this is a 3-variable function, which means we have to integrate with respect to x and y and z. But we have an option. We could do it in any order we choose, just like Fabini's theorem, assuming that all of these quantities are numeric. If the x's, y's, and z's all range within a constant frame, a constant cube, then we know that we're going to be able to integrate this function over that cubed region. We're not always going to be so lucky, but we'll take a look at that in a few minutes here. So let's just go ahead and start by choosing an order, and let's just say dz, dx, dy. Okay, so that would mean that if I was going to do dz, dx, dy, then y equals 1 to y equals 2 would be on the outside, and we'd integrate that with respect to y. But that's going to be the last piece, because before we do that, we're going to have to integrate from x equals 2 to x equals 3 dx. But before we could do that, we would have to integrate with respect to z, from z equals 0 to z equals 1 dz. but the function that we're actually integrating is the function 8xyz. So this is a fourth dimensional function, but we're integrating it over a three-dimensional space. So the first step here is just to integrate first with respect to z. So obviously 8x and y are constant, so this simply becomes 8xy times 1/2 z squared. So that's really just 4xyz squared, evaluated from 0 to 1. But notice that we're still going to have to integrate this with respect to x. And whatever we get there, we'll integrate with respect to y. Okay, well, evaluating this, remember these are z coordinates of 0 and 1. So that's just going to yield 4xy times 1 minus 0, or just 4xy. So now it's that quantity that we're going to be able to integrate with respect to x. All right, well, the integral with respect to x, obviously 4y is our constant, so the integral of x is 1/2 x squared, so that simply becomes 2x squared y, evaluated from 2 to 3. But keep in mind, we're not done, because after we finish that, we're going to have to integrate with respect to y. And whatever that integral is, integrate with respect to y. Okay, well, now we plug in 3 and 2. We apply the fundamental theorem. We plug these in for the x coordinates. So that's going to give me, plugging in 3 gives me 18y minus, now we plug in 2, and that's going to give me 8y. And therefore, we're integrating 10y. Okay, which means that we're integrating 10y, which is now finally down to a single variable with respect to y. And therefore, the integral gives me 5y squared. So 5y squared evaluated from 1 to 2. Plugging in 2 gives me 20. Plugging in 1 gives me 5. And therefore, this triple integral is evaluated to be 15. So anytime the limits of integration are all constants, we can easily just rearrange them in any order we want and integrate with respect to whatever variable we choose first. Now, in a very similar way to how we integrated double integrals or evaluated double integrals, we were able to use a double integral to calculate area. You might recall that the area of a region could be found by simply taking the integral from x equals a to x equals b of an integral of y coordinates, but remember that it's possible that the y coordinates were functions of x, because then they would turn into x coordinates anyway, which when we integrate the next time would become constant. But if we wanted to calculate this, that would mean that dy would have to be first, dx would have to be second, but more importantly, the integrand would have to be 1. Because now we were fixing the height at 1, and so the volume is typically length times width times height, where this is our area, okay, this is our dA. But now if I integrate the derivative of a, I get right back to area. Well, there's something very similar now when we deal with volume. We could actually find a volume using a triple integral. And again, I'll just deal with the x values first. So let's just say that it's still from x equals a to x equals b. And that's dx. But when we calculate using y, now we might have y values that aren't necessarily constants. Those y coordinates could be functions of the variable that follows. call that G2 of x and G1 of x. And that would be dy. But the last integral, or rather the first that we actually evaluate, would be z values or z coordinates. But notice that this z could be functions of whatever variables come after it. So once I integrate the first time, I should be down to x's and y's. So that must mean that z could actually be two variable functions of y. Let's call that f2 of xy. And that would be dz. But if we wanted this to equal volume, then that would also mean that the integrand would have to be, again, 1. So if we ever calculate volume, then we could calculate it simply by forcing this integrand, or the function, to be 1, so that now all that's left is our dv. And of course, the integral of the derivative of volume takes us right back to volume. So let's take a look at an example. Although we used a double integral in order to calculate a volume previously, that was in situations where we picked a region in the xy plane and mapped every point up to a particular location on that surface. The problem now is that if we want to find the volume of peculiar shapes that are bounded by multiple surfaces, we're not going to be able to use the same process of a double integral. So let's say that we wanted to find the volume enclosed by these two paraboloids. Okay, x squared plus 3y squared is opening upwards here. We could see that 8 minus x squared minus y squared is a paraboloid opening down. And so if you were to look at the region enclosed by both of those, it would be this kind of greenish region right in here. And we'd like to find the volume of that solid. So the way that we're going to do that is set up a triple integral. But before we could really find what the limits of integration are going to be, we're going to need to come up with our traces for each of these, for the xy, xz, and yz trace. So remember what that means. It means that if I'm going to find the xy trace, I would be standing up here on the z-axis looking downwards and trying to see what would that shape look like. If I wanted the xz trace, then I would be standing over here on the y-axis or somewhere along y and looking at the xz plane to see what that would look like. And likewise, the yz trace would be standing on the x-axis, looking over and seeing what the shape is. So we could maybe see pretty easily what the shape would look like here if we were standing on the x-axis, standing somewhere over here. We could see that it appears that it would be something like this shape here, like a parabola here, until it reaches some point, and then the parabola down below. So we're going to be trying to graph much more accurately. So let's go ahead and create these traces. So the way we do so is by setting a few, setting certain quantities equal to 0. So let's start off with the xz trace. Okay. So the xz trace is if we set y equal to 0. Okay. If we set y equal to 0, then that means that for the first function, we would end up getting z equals x squared. And for the second function, we would get z equals 8 minus x squared. And that's just by plugging in 0 for these two functions up here for y. I just set y equal to 0. And I now get two variable functions that I can graph. So let's graph both of those. So if this is the x-axis and the z-axis, then obviously one of those is going to cross up at 8. Okay. And the other one will open upwards from the origin. Okay. So I know that this will just curve upwards here. while the 8 minus x squared will start up top and curve downwards. And therefore, from the side, this is what we should notice if we were standing on the y-axis. And so this is going to help us to create the intervals for our functions, or for our triple integrals. What's most important here are what these intersection points are. Okay, so we should recognize that first of all, this green function is z equals 8 minus x squared. We could see that the purple function is just z equals x squared. But now let's say that we wanted to know where these functions crossed. Well, this is why we, again, just have to do a little bit of algebra by setting these two functions equal. So let's find our points of intersection. Okay, those points of intersection occur when 8 minus x, or when x squared is equal to 8 minus x squared, or in other words, when 2x squared equals 8, or when x squared equals 4, which means that x is plus or minus 2. So we could see that these coordinates here are going to be at -2 or +2. We could also find what that y coordinate is, or it's not y, I'm sorry, what the z coordinate is, by simply plugging into a -2 into our function. So we should be able to see that our y coordinate is 4. It helps to see these points of intersection because in a second we're going to start to create our triple integrals, and we're going to look at the graphs in order to determine what the lower and upper limits are going to be. Let's take a look at our YZ trace. Okay, the YZ trace is pretty simple as well. It just means set x equal to 0. Okay, and if I set x equal to 0, then that implies that I'm going to get z equals 3y squared for the first function. And I'm going to get z equals 8 minus y squared for the second function. Okay. Well, looking at the first function, we can see that, well, 8, it's going to obviously cross through 8 again. And it's going to be our standard kind of width here. But if you end up taking a look at 3y squared, that's going to be touching the origin, but it's going to be a much thinner parabola, so it'll be coming up a lot quicker. Okay, and so now we could see that from the other side, I should definitely make sure that I'm always labeling my axes. So this is the y-axis and the z-axis. So that means that if I was standing on the x-axis, I would notice a very similar shape, but it would be much thinner from one side. And so if we wanted to determine what those points of intersection were, then we'd have to set the functions equal again. So let's find the points of intersection. We're going to set 3y squared equal to 8 minus y squared. Or in other words, 4y squared equals 8, which implies that y squared is equal to 2. So the y coordinates are plus or minus the square root of 2. All right, so remember the y coordinates are on the y-axis down here, so that's at -√2, and that's at +√2. And it also can't hurt to find out exactly what the y value or the z value is at this location as well. And so if I plug in √2 to 3y squared, √2 squared is 2 times 3 gives me 6. And so we now already kind of have an idea about both directions, what they're going to look like, because most of the time we're not going to have the three-dimensional shapes. By the way, I pulled this for those of you that want to take a look at this online. This is from the website GeoGebra 3D. and it allows you to generate any three-dimensional objects, any three-dimensional surfaces. So now let's take a look at the XY trace. Okay, so the XY trace is typically when you set z equal to 0. Okay, and so traces are normally when you set the corresponding variable to 0, but it could also just be to any function. Okay. Now this is a very, because if we were to individually set each of our functions equal to 0, then that would mean that we would get 0 equals x squared plus 3y squared, which is really just a point. It's the origin. That's why sometimes it can be beneficial to not choose 0, but to maybe choose something else that would help us to recognize that this is in fact going to form an ellipse of some kind. And if I set the second one equal to 0, I get 0 equals 8 minus x squared minus y squared, which again would be a different ellipse. But if we were to take a look at this, that would just mean that if I was to look at z equals 0 here on this function, it would simply be a single point, while on this function, it would be an entire ellipse. But that's not really what we're interested in when we're looking down at the z-axis. What we've got to recognize is if we're looking straight down here from the z-axis, straight down from the z-axis back here, what is it going to look like when they intersect each other? Not when z is equal to 0, but when they intersect each other. So we do in fact set each z equal to 0, but because they're both equal to 0, that means we can in fact set these both equal to each other. So if we set them equal, then that means we get x squared plus 3y squared is equal to 8 minus x squared minus y squared. And this is going to tell us what the shape is that's not necessarily in the xy plane. What will the shape look like where they intersect? So if I add those terms to the other side, I get 2x squared plus 4y squared equals 8. And if I divide everything by 8, that ends up giving me x squared over 4 plus y squared over 2 is equal to 1, and we should recognize that as an ellipse. And so now we can see that even though each side separately over here is going to look like the intersection of two different parabolas, now from the top side, from the z-axis, we're going to see something much different. Okay? If this is the x and y axis, now I can see that in the x direction, I'm going to spread by the square root of 4 units, and in the y direction, I'm going to spread by the square root of 2 units. So that means that now I'm going to spread 2 units in this direction. But in this direction, I'll be spreading less because root 2 is about 1.4. And therefore, this is the XY trace. Now, what's most important to recognize here is when you are creating your triple integral, we're going to have to create some lower and upper bounds on each integral. And so that means that when we're looking at this, we need to be able to see what's the bottom and what's the top, what's the lowest piece and what's the highest piece. So in each direction, notice that in this case, the green curve is on top, the purple curve is on bottom. That would be the lower and upper limits. Likewise over here, the green is on top, purple is on the bottom. Those would be the upper and lower limits. But over here, we've got to be a little careful because now we've got to think about this as an upper function and separately a lower function. The ellipse itself is not actually a function. So what we need to do is we need to recognize that if I were to solve for y, this would end up giving me y equals the square root of 2 minus 1/2 x squared. And likewise, this would be the same thing, except that now it would be the negative of the square root of 2 minus 1/2 x squared. So I think by looking at these traces now, we're about ready to create our triple integral. Although there are different orders in which we could integrate this function or find the triple integral, find the volume, we're going to do it in terms of dz dy dx and dz dx dy. And I'll show you why. Because anytime you're given functions in terms of z equals a function of x and y, those are always the easiest ones to have on the inside. So we're just going to look at the fact that when you look at both of the traces involving z, you should be able to see that the green one is on top. Okay, the green one is on top, while the purple one is on bottom. The same thing you notice over here. The green one is on top, purple is on the bottom. So that must mean we're going to go from the parabola opening and paraboloid opening upwards to the paraboloid opening downwards. So let's go ahead and start with that and realize that for both of these, the inner limit of integration is going to be from z equals x squared plus 3y squared up to z equals 8 minus x squared minus y squared. So you can see that the limit of z is in terms of both y and x. And likewise over here, z is equal to x squared plus 3y squared, all the way up to the top surface, which is z equals 8 minus x squared minus y squared. All right, well, let's fill in the next piece that I think is easiest. The next piece is to fill in our x values over here. Now I know that these are x values because it's the outermost limit of integration. And so these are going to be both x coordinates, while over here, these will both be y coordinates. Because again, they are on the outside. Now lastly, we need to realize that the outermost limit of integration is going to have to be constant. So that means we need to know from the lowest x value to the highest x value, where is this graph going to intersect? So that just means we'll have to look at the two traces that involve x. So here's an x value, here's an x value. So what we should notice if we graphed correctly is that both of the x-axes extend from -2 to 2. -2 on the left to 2 on the right if we look in the xz direction. But obviously that's the same thing for our xy trace if we look in the x direction as well, from -2 to 2. So that means that my my x values are going to extend from -2 to 2. But what about our y values? Well, again, if we were to look at the y coordinates, we should recognize in the y direction here, the lowest it ever gets is -√2, the highest is √2, while over here, the lowest it ever gets is -√2, and the highest is still √2, which tells me that my constant limits for y are going to be from -√2 to +√2. And now the last thing I need to fill in is y equals something, which means over here we just need to fill in x equals something. But keep in mind that x is only able to be in terms of y. And likewise, y is only allowed to be in terms of x. It can only be in terms of the next variable in my integral. So you can now tell that from the equation in terms of x and y, we're going to be able to solve for y in terms of x, and we're going to be able to solve for x in terms of y. And so now if we look at it in terms of the y in terms of x, the blue is on the bottom, the yellow is on the top. But now if you're looking at it in terms of x in terms of y, now we would see that the x is on the left, while this x would be on the right. So let's fill those values in, and we've created our double integrals. This is the negative square root of 2 minus 1/2 x squared. I definitely should have given myself more space. And this here is 2 minus 1/2 x squared. So you can see that z is in terms of x and y is only in terms of x, and x is finally a constant. And now you can take a look at the other side over here and realize that this would be x equals the negative square root of 4 minus 2y squared, 2x equals the square root of 4 minus 2y squared. And using these two triple integrals, one or the other would allow us to find the volume of this solid. So we're now going to get some practice finding a triple integral with all of the limits of integration in all 6 orders. So we're going to start by just coming up with one, just so we can kind of construct this figure and understand how we're creating the limits of integration. So let's find the limits of integration in the order dy, dz, dx for evaluating the volume of the tetrahedron with vertices at these locations. So we're going to start off by plotting each of these. Okay, so let's go out to x equals 1, y equals 1, and z equals 1. Okay, and let's plot the first few points. So first of all, 0, 0, pretty straightforward point here. 0, 1, 0, that means 1 in the y direction. So here's another point over here. 1, 1, 0, so that's still the z value of 0, but it's going to be at the point in the xy plane, 1, 1. Okay, and so this is going to be the point 1, 1, 0. Okay, we can go ahead and label them as we go, I suppose. 1, 1, 0, and of course 0, 0, 0. And 0, 0, 1, 0. And the last step here is to plot 0, 1, 1. So that means that I'm moving 0 in the x direction, but I'm going over to 1 on this y-axis. And I'm going upward to 1 unit. So now I've got the corners of this figure. And we want to now draw this figure by connecting all of the dots. Well, I'm going to take you through the different ways to approach writing all 6 iterations of this triple integral. We know that whenever we're writing out our triple integral, this last variable will always be constant. So that means that all we have to do here is just go from, for the x value, let's start with just this x coordinate, and realize that within this figure that we see on this right side over here, the x coordinates extend from 0 to 1. As we move through from 0 to 1, you can see that you're always going to get some point in that figure. In the y direction, it also extends from 0 to 1. And in the z direction, it also extends from 0 to 1. So this one's relatively simple just because of the fact that all directions are going to be the same. And so we could see that in this case, x is equal to 0 to x equals 1. And we could also see way down here that x would have to extend from 0 to 1 as well. Now, if we look at the y coordinates here would extend from 0 to 1 as well. while the y coordinates in this problem extend from 0 to 1 as well. And finally, because both of these are in terms of z at the very end, we see that these are going to extend from z equals 0 to z equals 1. And so typically the values in the last integral are going to be relatively simple based off of your figure or based off of your diagram to be able to figure out what those constant values are going to be. So now we've got to realize that the next integral right here is going to have to be in terms of the prior variable. Or in other words, since this here, the middle integral is z, I need z to be in terms of x and x to be in terms of z. So those are going to be relatively easy. Once I find one, I just manipulate the equation to find the other. Y would have to be in terms of z, and z would have to be in terms of y. X would have to be in terms of y, or y would have to be in terms of x. Now I say that as the most variables that could be in there. For instance, in this case, z is a function of x for the top one, but z could also be a constant. So it could be either x or a constant. In this case, I could have x in terms of z, or x equals a constant. Y in terms of z, or y equals a constant. So we have to start thinking a little bit more, a little bit better here by realizing that for the zx, we need to be describing how does z change as x changes. Now, in a way, we need to determine what the xz trace is going to look like. But we could really see from this figure that the xz trace is really not even there. There's nothing in the xz plane over here. So what we want to do instead is we want to project that figure as if we were standing on the y-axis. We want to project that figure over onto the xz plane. So what we're going to do is we're going to create this little shadow. So you could see that if I was to project this point down at the bottom here onto the xz plane, it would end up right here. If we were to project this point way up top onto the xz plane, it would end up right here. And so what we have here is this trace, or rather this shadow, okay, that's going to be formed right here. And from that shadow on the xz plane, because if you look at the yz plane, you could see that there is in fact a plane on the yz plane. If you see the xy plane, notice there is something down on the xy plane. But in this case, there's nothing on the xz plane. So there's no way for us to be able to see exactly how z changes as x changes. We now have our shadow of the object in the xz plane. And we want to determine what the equation is in terms of x and z. So let's just think about this on our xz plane, right? It would touch at z equals 1, it would touch at x equals 1, and it would cut through. So that's nothing more than just z equals the y-intercept of 1 and a slope of 1 minus x. So notice that this figure here, this plane, is the plane z equals 1 minus x. So in other words, when y is equal to 0, we're going to see the plane z equals 1 minus x. So let's think about how this extends then. So how does z change as x changes? As x keeps moving through from 0 to 1, z changes from z equals 0 up to the line. At a different location of x, it extends from 0 up to the line. And so we could see that now, as x changes, that would mean that that z would extend from 0 to 1 minus x. And if I were to manipulate things in terms of x's and z's, now I would see that as z changes from 0 to 1, x changes from 0 to the line. So we really just have to rewrite this in terms of x equals 1 minus z. And that's why we can now go down here and realize that x is equal to 1 minus z. So x equals 0 up to x equals 1 minus z. So now let's look in terms of y and z, okay? So now we're looking in the yz plane, just this plane right over here, okay? So now I could see that as z changes from 0 to 1, y changes from something out to something else, right? And that's what we're trying to do here. So we're trying to find out, how does y change? And while down here, we're trying to figure out how z changes. And lastly, how does x change? And how does y change? So we essentially need to just look at each of those traces to determine how those are going to change. We look at the three-dimensional figure, but as we mentioned before, it could really help to actually just look in 2 dimensions at a time. So that's why we're going to go ahead and graph our xy, xz, and yz traces. So let's start with the one that we've already done. We already knew that our xz trace was going to have a y-intercept or a z-intercept at 1 and a z-intercept or an x-intercept at 1. And therefore, this right here is going to be our xz trace, as we should be able to see from this piece right up here. All right, so now let's look at our xy trace. We're only looking down in this little triangle in the xy plane. So now you got to realize that there is a xy intercept at 0, 0, obviously. There's a y-intercept at 1, but there is no x-intercept. Turns out that the x value is going to be out here at 1, 1. And so what we have now is this trace. And that's what we would see if we were standing up on the z-axis. And lastly, if we were to look at the yz trace, now we're only looking at the piece in the yz plane. And so again, we could see that there is obviously, just like the last problem here, there was a y-intercept at 1, only now it's going to be on the horizontal axis. But there is no z-intercept. Instead, it touches the origin, and it touches the point at 1, 1. So now we can see that this is the trace in the yz direction. Well, this is going to be beneficial because we can now end up writing out what each of our edges are. So we can see that this edge over on the left side is going to be x equals 0. We can see that this horizontal edge up top is y equals 1. And because this has a slope of 1, this is just y equals x. And we could see the same thing here. We could see that this is x equals 0. We could see that this is z equals 0. We can see that this is the line with a z-intercept of 1 and a slope of -1, so 1 minus x. And likewise, this is z equals 0. This is y equals 1. And finally, the line z equals y. So what we're now looking at here, if we were to go to this region right here, okay, we want to look at y in terms of z. So we want to now determine, how does y change as z changes? Okay, well, y extends as I move as I move through my dx, dy, dz. As I move through this, I could see that y begins at 0. And as y changes, as I keep changing my y values, it's extending up to z. Z equals y or y equals z. Well, again, as y changes from 0 to 1, we can see that z is going to change from 0 up to y. So that means that as y changes from 0 to 1, z changes from 0 up to y. Well, let's look at the other direction. This is saying as z changes from 0 to 1, as z changes from 0 to 1, if I were to pick one particular z value, like right here, how exactly would y change? Well, look at this. As y enters here and leaves here, I should be able to see that it's going to enter at y equals z, and it's going to leave at y equals 1. And so we know that this is going to be from y equals, where are we at? Here. This is going to change from y equals z out to y equals 1. So now let's take a look at this one. When y changes from 0 to 1, how does x change? So that's when we're looking at our xy trace. Okay? So as y changes from 0 to 1, x changes from 0 out to y. X equals y. So notice that that's going to say that when y changes from 0 to 1, x changes from 0 up to y. And how about in the other direction? As x changes from 0 to 1, so pick any x value between 0 and 1, y changes from this entrance point, which is x, to this exit point, which is 1. So y changes from x to 1, which is why we now have our full second integral filled in. So now we just have to figure out what's going to happen on these outer ones. Okay, so now we realize that these are going to have the innermost integral is obviously z equals. Here we also get z. On this next one, we get x values. And in order to figure out this innermost limit, we really need to think three-dimensionally at this point. And this last one is y equals as well. Okay, so I'd like to just start with one of these, okay? Now, basically, in order to fill in our innermost limit, the way that we're typically going to do that is we're going to look in the other two directions. So if I'm looking in if I'm trying to figure out what happens with the y value, then I'm going to start with the xz plane. So if I look at the xz plane, then I'm saying if I were to take this xz plane and start moving it forward in the y direction, where does that enter the shape and where does it leave the shape? Okay, so that's essentially what we're looking at there. So I can see that it's going to pick some point here, and as I move parallel to the y, it's going to enter this blue plane, and it's going to continue through, and it's going to leave on the back side of this. And so anywhere that's in the xz plane, anytime the y is changing, that means that the first thing it's entering is this plane, and then it's leaving this plane back here. So our job then, first of all, is to figure out what the equation of that plane is. Now, most of the time, you're going to be given what that plane is, but I didn't give it to you. I'd like to kind of think through how we would actually find what that plane is. So remember that the equation of a plane in general is ax plus by plus cz equals some constant. And remember, the way that we find that is to find an orthogonal vector that sticks out of this orthogonal to that plane. Okay? Well, before we could do that, we need to have a cross product of two vectors. So let's just start off by coming up with two vectors. Let's say we look at this vector right here, extending from the origin, and let's look at this vector right here, extending from the origin. So if we've got these two vectors extending from the origin here, then we could just find the cross product between those. Okay, so let's call this U, let's call this V. All right, well, notice that since they're both starting at the origin, V is the vector 0, 1, 1, and U is the vector 1, 1, 0. So let's go ahead and find U cross V. So U cross V is going to be equal to the determinant so the determinant of vector U, which is 1, 1, 0, with the vector V, which is 0, 1, 1. So 1, 1, 0 and 0, 1, 1. And so this is going to tell me the values of A, B, and C. So in the I direction, we get 1I minus 0J, okay, minus, now in the J direction, we get 1 minus 0, which is also 1J. And finally, we end up getting in the K direction, we get 1 minus 0, which is also plus 1K. So I know that that blue plane is simply equal, or the blue plane is 1 times x minus 0 minus 1 times y minus 0 plus 1 times z minus 0. And the reason I'm just picking 0, 0, 0 is because it's the easiest and it's on the plane. And so notice the plane is just x minus y plus z equals 0. So this plane up here then is actually going to be the plane x minus y plus z equals 0. But more importantly, we could actually solve for each of the variables separately. We could realize that x is equal to y minus z, which is going to be helpful in filling in these limits of integration. Y is equal to x plus z. And finally, z is equal to y minus x. We just manipulated it a bit. Well, the nice part about that is, as I think this three-dimensionally, now all I have to do is fill in what the corresponding x, y, or z is based on whether I need x, y, or z in this region here. So let's extend this. So let's think about how this works. So as I start in the xz plane, this is going to enter the blue plane and it will leave y equals 1. So that means that this is going to enter the plane at y equals x plus z, and it's going to leave at y equals 1. But because x and z come after it in both of these, it's not going to affect the original integral. And so notice that these limits, once you find one, you found the other. Okay, so that means that this is going to be from y equals x plus z to y equals 1 as well. So now let's look in the other direction. So starting off with the yz plane, how does x change? Well, notice that this is the yz plane back here. And we're basically looking at the fact that this solid touches the yz plane. So as I move parallel to the x-axis, pick some place in that yz plane and move towards the x direction, it's going to start at x equals 0 and it's going to exit the blue plane. So that's why it's going to start at x equals 0 and exit the plane, which is x equals y minus z. And this will also be 0 and y minus z. And lastly, if we wanted to look in the xy direction, in order to determine what's happening with z, the xy plane is this piece down here. So as I pick any point in that region and start extending upwards, it's going to eventually leave the blue plane. And so notice that it's going to extend from z equals 0 up to that plane. So it's going to extend from z equals 0 up to z equals y minus x. And therefore this is y minus x. And for our last one, we see that it's also z equals 0 to z equals y minus x. So we should always notice that when we're setting up our limits of integration, the outer limits of integration will be constant. The middle limits of integration will be in terms of, they'll either be constants or they will be in terms of the variable in the last limit. And the innermost will be in terms of the two variables that come after it. So y will be in terms of x and z, x will be in terms of y and z will be in terms of x and y, or they will be constants. And so it's important for us to be able to come up with all 6 orders of integration for a triple integral, and we can pick any one of these that looks easiest in order to calculate to find the actual volume of that tetrahedron. So let's pick one of those. I feel that the first one is probably the hardest simply because it has the least amount of zeros. So let's go ahead and pick this one. Okay. And so we're going to use dy, dz, dx. Okay. So we'd like to find the integral. Okay, the integral from 0 to 1 of the integral from 0 to 1 minus x of the integral from x plus z to 1 of dy, dz, dx. So I like to put x equals and y equals and z equals just to help us understand what those are, but most of the time you're not going to see those values. You're just going to have to recognize that x is referring to these limits, z refers to these limits, and y refers to these limits. So we're going to integrate with respect to y first. The integral of 1 dy is y, evaluated from x plus z to 1. So that's going to give us 1 minus the quantity x plus z, which is 1 minus x minus z. Okay, but notice that each of those is now going to have to be integrated from 0 to 1 minus x for z, and from 0 to 1 for x. So the next thing to do here is to integrate in terms of z, dz. Okay, so if I were to integrate this function with respect to z, then that becomes z minus xz minus 1/2 z squared. But notice that that's now integrated from 0 to 1 minus x. And whatever that becomes, it should only be in terms of x by that point, which is why the outer limit is a constant. So let's plug this in. If I plug in 0 for all the z's, then notice that that's going to cancel out each of the terms. So all I'm left with right here is going to be 1 minus x times 1 minus x minus 1/2 times 1 minus x squared. And whatever that becomes or simplifies to, I'm now going to integrate with respect to x because it's the last variable. All right, well, we should be able to simplify this a little bit. So let's work on doing that. So that becomes 1 minus x plus x squared. And then if I expand 1 minus x quantity squared and multiply by 1/2, we get minus 1/2. We get minus 2x times negative 1/2 is plus x. And finally, x squared times negative 1/2 is negative 1/2 x squared. We're going to evaluate that from 0 to 1. So simplifying gives me 1 minus 1/2, which is 1/2. Negative x plus x cancels, so we're left with minus x. And finally, x squared minus 1/2 x squared is plus 1/2 x squared. And finally, integrate this with respect to x. All right, well, that must mean that we get 1/2 x. Next one, we integrate to get negative 1/2 x squared. Next one, we integrate to get plus 1/6 x to the third. And if you evaluate that from 0 to 1, notice that plugging in 0 for all the x's cancels it. So all we're left with is 1/2 minus 1/2 plus 1/6, which means that my volume of this tetrahedron is 1/6. And so we could have chosen any one of the 6 different iterations of this triple integral, but we ended up deciding to choose, well, the first one that we wrote, dy dz dx. And this should, but either one, any of the 6 that we choose should still give us the same value of the volume of 1/6.